Hi, my name is Kalen Patton, and I'm going to be talking to you today about the Prague dimension of random graphs. This is part of a joint work that I did with Guo and Dr. Lutz Warnke. So to start off, I want to introduce the concept of Prague dimension. So Prague dimension is a notion of graph dimension introduced by Nesetrill, Klotcher, and Riddell in the 1970s. And it has many equivalent definitions, although perhaps the most natural definition has to deal with ways of embedding a graph G in a product of complete graphs. The definition that we are going to use that's most useful for us is this one given here based on click edge coverings. So what this definition says is it says that the Prague dimension of G is equal to the least integer k such that there's a k-colorable click edge covering of G bar. So what does that mean? That means that if we look at the graph G bar, the conjugate graph, first we can find a click edge covering, meaning we can find a set of clicks that cover all edges of G bar, and then we can color this, set of clicks in such a way that we use at most k colors, and each pair of clicks, that intersect at a vertex must be colored distinct colors. So to simplify this definition a little bit, we're also going to introduce this auxiliary parameter called the click color number, which is just defined as the Prague dimension of the conjugate graph. This just allows us to remove this conjugacy from the definition and deal directly with click edge coverings of the graph G. Okay, and so now to see an example of this click color number, we can look at this graph here at the bottom. So this graph, one way that we can get an upper bound on the click color number is we can first find a click edge covering and then color it with a few colors. So we can see this over here on the right. We find a click edge covering using 6 clicks, and then we can color this click edge covering properly using 3 colors. So that tells us that the click color number of this graph must be at most 3. And a natural question we might ask is, well, is it actually equal to 3? Can there be a click edge covering that is 2 colorable? And we can determine that this actually can't be the case by finding a lower bound by looking at this vertex here. So if we look at this vertex, first we can convince ourselves that there's no way to cover all the edges incident to this vertex using only 2 clicks, right? The only way that we can cover all the edges incident to this vertex is by using at least 3 clicks. And then that means that any click edge covering must contain at least 3 clicks that all contain the same vertex. And therefore, we need to use at least 3 colors to color any click edge covering of this graph. And then so the click color number must be at least 3, and therefore from our upper bound we know it's exactly 3. Okay, and so now this brings us to the main question that we seek to answer, which is how does the Prague dimension, or equivalently the click color number, behave for the random graph GNP? In particular, it has been conjectured by Freudian contour that with high probability, the Prague dimension of GNP should be on the order of n over log n for constant p. So in order to examine this conjecture, the first thing we might note is that it suffices to instead just look at the click color number. Because if we can show that the click color number of GNP is on the order of n over log n with high probability, then it also implies that the Prague dimension is also on the same order, since the Prague dimension of GNP is simply the click color number of the conjugate graph, but the conjugate graph of GNP is distributed like Gn 1 minus p. So for p if we can show this is true for p in the range 0 to 1, then it also shows that for the same range of p, the result holds for the Prague dimension. Okay, so looking now at the click color number, the first thing we can look at is devising a lower bound. And the lower bound, it turns out, is actually fairly simple. We can use pretty much the same strategy that we used for looking at a lower bound on this graph here. So the idea is going to be that we're going to look at how many clicks must be present at a particular vertex. And in particular, we can look at the vertex of maximum degree. So the vertex of maximum degree in GNP is going to have delta GNP edges incident to it. And any click which contains this vertex can cover at most omega GNP minus 1 many of these edges. So omega GNP being the size of the largest click in GNP. And so because of that, we need to at least this quotient here, delta GNP over omega GNP minus 1, many clicks present at this one vertex in order to cover all edges incident to it. So and then because all of these clicks must be colored with different colors, it tells us that in any click edge covering, we need at least this many colors, since this is how many clicks all share the same vertex. So that gives us a lower bound on the click color number, which then, if we use known estimates for these two parameters, delta GNP and omega GNP, gives us a lower bound on the order of n over log n. Okay, and then another thing that this lower bound sort of highlights is it highlights a potential difficulty in finding a corresponding upper bound. Because if we want to find an upper bound that matches this lower bound, it tells us that we need to be able to cover GNP first with clicks of size of mostly nearly maximum size, so mostly clicks of size on the order of log n. And then we need to color these clicks in such a way that we can color them with on the order of n over log n colors. So both our covering and our coloring need to be very tight in terms of the size of the clicks that we use and how many colors we use. Okay, and so now this brings us to our main theorem, which essentially answers the conjecture by Ferretti contour in the affirmative. So it says that we can indeed find this upper bound, and we do get that with high probability. The click color number of GNP is typically on the order of n over log n. So as I mentioned before, there's sort of two main steps to proving this upper bound. So first, we need to find this click covering of GNP, which needs to be fairly efficient in that it uses mostly clicks of size on the order of log n. And then the next thing we need to do is we need to find also a coloring of this click covering that is also efficient in that it uses at most on the order of n over log n colors. So there's kind of two steps to this proof. The first step we can solve using this nibble algorithm approach. So this is a sort of a standard approach. What we're going to do is we're going to start off with GNP and iteratively sample random sets of clicks of large size. And then we remove the edges that are covered from our consideration, and then we sample another set of large clicks from the remaining edges. And we repeat this process until we've covered all clicks in GNP, all edges in GNP with clicks. And we get this click edge covering, which is expressed as a union of each of these partial click edge coverings that are returned in each step of the algorithm. Okay, and then for our next step for coloring this click edge covering, our basic strategy will be to color the click covering C by coloring each of these partial click coverings with a disjoint set of colors. And so when we color each of these with a disjoint set of colors, the first thing we can check is that the sum of the maximum degrees in each partial click edge covering sums to a value on the order of n over log n. And one thing to mention here, when I say maximum degree of a set of clicks, I mean the maximum degree of the set of clicks when we view them as a hypergraph. So a set of clicks, we can view the clicks as hyperedges, and therefore we can view a set of clicks as a hypergraph on this set of n vertices. And so when I use notation like this, referring to hypergraph parameters on these partial click edge coverings, just know that that's what I mean. I mean the parameter when you view this as a hypergraph. So because we know that the sum of the maximum degrees is on the order of n over log n, all that we really need to say is that we want to be able to say that the chromatic index of each of these partial click coverings is on the order of its maximum degree. Because then we can use this estimate, where we estimate the chromatic index of the entire covering by the sum of the chromatic indices of each partial click covering, again saying that we color each of these partial coverings with a disjoint set of colors. And then we could say that the chromatic index of each partial covering is on the order of its maximum degree, which we know then sums to something on the order of n over log n. So this is the general proof strategy, and going forward, I want to spend most of the time talking about this second part. So I'm going to briefly go over the first part, the nibble algorithm, But then I want to spend most of the time talking about the second part, in particular this estimate here, that the chromatic index is on the order of the maximum degree, because that's where we're going to employ our main new novel result, which is a new hypergraph coloring theorem. Okay, so like I said, the first part of our proof is this semi-random nibble algorithm, and it works as follows. We start off with GNP, and we construct this decreasing sequence of subgraphs, G0, G1 up to G big I. The way we do this is starting with G0, we randomly sample a set of large clicks, so clicks of size on the order log n. We remove them from the graph, or we remove the edges of them from the graph to then get the graph G1. And then we repeat the process. So we sample randomly a set of large clicks from G1, we add them to our covering as C1, and we remove the edges of those clicks to get G2. And we repeat this process, sampling clicks and removing their edges, until we get a graph G big I, which is so sparse that we simply can take all remaining edges of our graph as clicks of size 2. And we add them to our click covering as C big I. And then of course we take our total click covering C as the union of the clicks selected at each step of the process, and we get a efficient click covering. Okay, so this brings us now to the second part of our proof, in which we want to show that the chromatic index of this click edge covering that we just generated is indeed on the order of n over log n. And as I mentioned earlier, the main component in this second result is this intermediate estimate that the chromatic index of each CI is at most on the order of its maximum degree. So in particular, if we first look at the case when I equals big I, so the last step of our algorithm, we note that we can simply get the result we want by applying Ising's theorem. And this is because, if we remember, in the last step of the algorithm, all of the clicks that we add are simply clicks of size 2, so they're essentially just edges. And therefore, the hypergraph that consists of these clicks is simply a usual graph, and therefore Ising's theorem can apply. However, for all other I, we have edges of size more than 2, up to even log n. So for these CI, we want to apply a result like Puppinger-Spencer. Puppinger-Spencer is this theorem given at the bottom, which essentially extends Ising's theorem to the setting of hypergraphs. So Puppinger-Spencer says that for constant k, any hypergraph that is k uniform and also is sufficiently regular and has small codegree then satisfies that its chromatic index is at most 1 plus epsilon times its maximum degree. So this is saying that the chromatic index is indeed on the order of the maximum degree, which is exactly what we want. However, it turns out we can't apply Puppinger-Spencer directly because we run into this small snag, that Puppinger-Spencer only applies to hypergraphs with constant edge uniformity k. And remember that in our partial click coverings CI, we can have clicks potentially of size up to log n. So this is a problem, but it turns out that we can actually overcome this if we exploit the fact that each CI is not simply an arbitrary hypergraph, but is actually a randomly sampled set of clicks. And it's this randomness in the determination of CI that allows us to extend Puppinger-Spencer's result up to k on the order of log n for these particular hypergraphs. And so this result is stated formally here in our main auxiliary result about the chromatic index of random subhypergraphs. This says that if we have a hypergraph H that is k uniform and satisfies these requirements, so k must be at most b times log n for some constant b, and then we have that H must be approximately regular and have small codegree, then a random subhypergraph denoted HM, which consists of m randomly sampled edges, m being much smaller than the total number of edges, then HM satisfies the chromatic index is at most 1 plus delta times its maximum degree, where delta is this other parameter that's proportional to b. And so the key point is that this edge uniformity requirement now allows for k up to the order of log n. Okay, and so if we analyze what we're saying here in this theorem, we can think of two main cases for the edge uniformity k. First, if k is much smaller than log n, then we can apply this, this theorem with b chosen to be arbitrarily small. And therefore, we can make delta arbitrarily small, and we can regain this Purkinje-Spencer type result, that the chromatic index is at most 1 plus epsilon times the maximum degree. However, in addition, if k is on the order of log n, then although b may not be very small, we can still choose b to be constant. And therefore we get delta that is constant, and we get that the chromatic index of hm is on the order of the maximum degree. And this is the exact thing that we want to use for hypergraphs that have edges of size on the order of log n. We can still get that the chromatic index is on the order of the maximum degree, as long as we also satisfy these sort of auxiliary requirements, but those are verifiable for our purposes. Okay, so with this result, we have now our main theorem. And so now, with the brief time I have left, I want to quickly go over the general proof strategy for this auxiliary hypergraph coloring result. So the proof is based on an analysis of a natural random greedy coloring algorithm, which starts off with this carefully chosen set number of colors. In this algorithm, we're going to randomly sample edges of H and then color them with randomly chosen colors from those still available at H. Okay, so now this concludes the proof of our main theorem. And in the brief time I have left, I want to quickly go over the general proof strategy for our auxiliary hypergraph coloring result. So the proof of this result is based on an analysis of a natural random greedy coloring algorithm. So in this algorithm, we start off with the hypergraph H and some fixed set of colors, and we randomly sample edges of H and then apply to them a randomly chosen color that does not conflict with any previously assigned colors. And by analyzing this algorithm with a differential equation method, we can show that the number of colors available to color any given edge follows a trajectory which ensures that our algorithm can successfully color m random edges in H, which then gives us our result. So to see how this algorithm works in practice, we will show it by this example here. So we start off with a hypergraph H, which I just chose the affine plane of order 3 as an example. And we start off with a set of colors. So here, we'll say our set of colors is red, blue, green, and yellow. Then our random greedy algorithm will first randomly select an edge of H, and then look at all available colors at this edge. So because we haven't colored anything yet, all colors are still available. So then we randomly choose one to assign to this edge, say red. And we continue like this. So we'll sample an edge uniformly at random, and then we'll look at the set of available colors. Because this edge doesn't intersect any previously colored edges, all colors are still available, so we simply pick a color uniformly at random. Now if we next sample this edge intersects a red edge and a green edge, so the only available colors are blue and yellow. So our algorithm will pick from among these two available colors uniformly at random, and then assign that color to the edge, so say blue. And then we just continue like this. So if we sample this edge, the set of available colors is red, green, yellow, so we pick one uniformly at random to assign, say red. And then for this edge, because it intersects a blue, green, and red edge, the only available color is yellow, so that will be the color assigned by the algorithm. And then if our algorithm terminates here, then we have this set of 5 colored edges make up our random subhypergraph HM, and then we have the coloring given by the algorithm of HM. Okay, so that's all I have for you today. So to conclude, we began by considering a conjecture by Freudian contour about the Prague dimension of the random graph GNP. And we find that in order to prove this conjecture, we will make use of this new extension of Purkinje-Spencer for random subhypergraphs, which allows for edge uniformities up to on the order of log n for random subhypergraphs. And so some remaining questions we have about this are, first, can we say something similar for general hypergraphs? So for instance, can we extend Purkinje-Spencer up to O of log n size edges in general? And then in the random setting, can we extend beyond O of log n? So can we extend for edges maybe of size greater than O of log n when we're considering random subhypergraphs? Okay, that is all I have for you today. I hope you learned something, and thank you very much for listening.